NEC 310.15 addresses the requirements for neutral conductors in electrical circuits concerning ampacity adjustment. Specifically, 310.15 states that a neutral conductor carrying only the unbalanced current from other conductors of the same circuit is not required to be counted when applying the provisions of 310.15b2. 310.15b2 deals with ampacity adjustment factors for conductors in a raceway or cable with multiple current-carrying conductors. However, there is an important exception to this rule. A neutral conductor that is used as a feeder must be counted when applying the provisions of 310.15b2. To understand this, it's important to define a few key terms. Firstly, a neutral conductor is a conductor that carries the unbalanced current in a three-wire or multi-wire circuit. In a balanced three-phase system, the neutral conductor ideally carries very little or no current. However, in reality, loads are rarely perfectly balanced, and the neutral conductor will carry some current. Secondly, unbalanced current refers to the difference in current between the phase conductors in a multi-wire circuit. This current flows back to the source through the neutral conductor. Thirdly, a feeder is a circuit conductor or conductors extending from the service equipment to a subpanel or branch circuit distribution point. Feeders carry the total current supplying multiple branch circuits. Now let's delve into the exception. When a neutral conductor serves as a feeder, it's treated differently because it's carrying a substantial amount of current that's not solely the result of unbalanced loads on a single circuit. The code recognizes that this feeder neutral's current carrying capacity needs to be considered when determining ampacity adjustments. The reason for counting the feeder neutral in ampacity calculations is to prevent overheating and potential fire hazards. When multiple current-carrying conductors are bundled together in a raceway or cable, the heat generated by each conductor can raise the overall temperature inside the raceway. This increased temperature reduces the ampacity of the conductors. 310.15b2 provides adjustment factors to account for this dirting. If a feeder neutral carrying a significant amount of current were not counted, the conductors could be overloaded, leading to insulation damage and potential failure. Let's illustrate this with an example. Imagine a 120/208 volt, three-phase, four-wire feeder supplying several single-phase branch circuits in an office building. The feeder consists of three-phase conductors and a neutral conductor. The branch circuits supply lighting, receptacles, and small appliances. If the loads on the three phases are not perfectly balanced, the neutral conductor will carry the unbalanced current. If this neutral conductor is considered a feeder neutral because it is supplying multiple branch circuits, then it must be counted as a current-carrying conductor when applying the adjustment factors in 310.15b2. For instance, if the feeder conductors are installed in a raceway with a total of 4 current-carrying conductors including the neutral, the ampacity of each conductor must be adjusted according to the table in 310.15b2. This adjustment factor will typically reduce the allowable ampacity of the conductors. On the other hand, if the neutral conductor were part of a single multi-wire branch circuit carrying only the unbalanced current of that circuit, then it would not need to be counted as a current-carrying conductor for ampacity adjustment purposes. The key distinction lies in whether the neutral is serving as a feeder supplying multiple branch circuits or simply carrying the unbalanced current of a single circuit. To further clarify, let's discuss some practical scenarios. Scenario 1: a multi-wire branch circuit supplying lighting fixtures. Consider 120/240 volt single-phase 3-wire branch circuit supplying recessed lighting fixtures in a room. The circuit consists of 2 hot conductors and a neutral conductor. The lighting fixtures are connected to both hot conductors, and the neutral conductor carries the unbalanced current. In this case, the neutral conductor is not considered a feeder neutral because it's part of a single branch circuit. Therefore, it does not need to be counted as a current-carrying conductor when applying the ampacity adjustment factors in 310.15b2. Scenario 2: a feeder supplying a subpanel. Imagine a 480/277 volt, three-phase, four-wire feeder supplying a subpanel in a manufacturing facility. The subpanel distributes power to various machines and equipment. The feeder consists of 3 phase conductors and a neutral conductor. In this scenario, the neutral conductor is considered a feeder neutral because it's supplying a subpole that serves multiple branch circuits. Therefore, it must be counted as a current carrying conductor when applying the ampacity adjustment factors in 310.15 B2. Understanding the distinction between these scenarios is crucial for ensuring compliance with the NEC and maintaining a safe electrical installation. Failure to properly account for the neutral conductor in ampacity calculations can lead to overloaded conductors, overheating, and potentially fire hazards. It is important to consult with a qualified electrical engineer or electrician to determine the appropriate ampacity adjustments for specific installations. Additionally, it's important to note that the NEC is updated regularly and it's essential to stay current with the latest revisions. Changes to the code can affect the requirements for neutral conductors and ampacity adjustments. In summary, NEC 310.15 B4 provides specific guidelines for neutral conductors in electrical circuits. While a neutral conductor carrying only the unbalanced current from other conductors of the same circuit is not required to be counted for ampacity adjustment purposes, a neutral conductor serving as a feeder must be counted. This exception is crucial for ensuring the safety and reliability of electrical systems. Remember to carefully evaluate the specific circumstances of each installation and consult with qualified professionals when necessary. Always prioritize safety and compliance with the NEC to prevent electrical hazards. By understanding and applying these principles, one can design and install electrical systems that meet the requirements of the NEC and provide safe and reliable power distribution. It's not only a matter of compliance, but also a matter of safety. Overloaded conductors can cause fires, damage equipment, and put people at risk. By following the code and using good engineering practices, these risks can be minimized. Remember that the NEC is a minimum standard, and in some cases, it may be necessary to exceed the code requirements to ensure a safe and reliable installation. Factors such as ambient temperature, conductor material, and installation methods can all affect the ampacity of conductors, and it's important to consider these factors when designing an electrical system. In addition to 310.15 B4, there are other sections of the NEC that address neutral conductors. For example, 220.61 covers the sizing of neutral conductors for services and feeders. This section provides specific rules for calculating the neutral load based on the type of loads being served. It's important to consider all applicable sections of the NEC when designing an electrical system. The NEC is a complex document, and it's essential to have a thorough understanding of the code to ensure compliance. If one is not familiar with the NEC, it's best to consult with a qualified electrical engineer or electrician. They can provide guidance on the proper application of the code and help ensure that the electrical system is safe and reliable. Furthermore, the interpretation of the NEC can vary depending on the local jurisdiction. Local codes and amendments may add additional requirements or modify the existing requirements in the NEC. It's essential to be aware of these local codes and amendments when designing an electrical system. Local authorities having jurisdiction are responsible for enforcing the NEC and local codes. They can provide clarification on the interpretation of the code and help ensure that electrical installations meet the required standards. Regular inspections by local authorities can also help identify potential hazards and ensure that electrical systems are maintained in a safe condition. Continuing education is also crucial for staying up to date with the latest changes to the NEC and best practices in electrical design and installation. The electrical industry is constantly evolving, and new technologies and techniques are being developed. By participating in continuing education courses and seminars, one can stay informed about these changes and improve the skills and knowledge. Moreover, the application of 310.15 B4 and related NEC articles often involves practical considerations that go beyond the theoretical understanding of the rules. For instance, the actual loading on a neutral conductor can be difficult to predict accurately, especially in complex electrical systems with a variety of different types of loads. In such cases, it may be prudent to overestimate the neutral load to ensure that the conductor is adequately sized. The use of load monitoring equipment can also help to determine the actual loading on a neutral conductor and identify any potential imbalances. This information can be used to optimize the design of the electrical system and ensure that the neutral conductor is not overloaded. Furthermore, the physical installation of conductors can also affect their ampacity. Factors such as the proximity of conductors to each other, the type of insulation used, and the presence of thermal insulation can all affect the heat dissipation of conductors and their ability to carry current safely. The NEC provides guidelines for directing conductors based on these factors. It's important to follow these guidelines carefully to ensure that conductors are not overloaded. In addition to the technical aspects of 310.15 B4, it's also important to consider the legal and contractual implications of electrical work. The electrical contractors are responsible for ensuring that their work complies with the NEC and all applicable local codes. Failure to do so can result in fines, penalties, and legal liability. It's also important to have a clear understanding of the scope of work and the responsibilities of each party involved in a project. Contracts should clearly define the electrical requirements and the standards to which the work must be performed. Proper documentation of electrical work is also essential. This includes drawings, specifications, calculations, and inspection reports. This documentation can be used to demonstrate compliance with the NEC and to provide a record of the work that was performed. In conclusion, understanding and applying NEC 310.15 B4 requires a combination of technical knowledge, practical experience, and attention to detail. It's important to stay up to date with the latest changes to the code, to consult with qualified professionals when necessary, and to follow good engineering practices. By doing so, one can help ensure the safety and reliability of electrical systems and prevent electrical hazards.